Hello everyone, welcome to your next chapter and section. Today we are going to learn a lot about machine learning. We had a little bit of a taste of machine learning in our natural language processing section, and we also got a bit of an understanding of machine learning even through our basics of statistics class, because without that foundational knowledge, there's no way you can take on an intense concept like machine learning, because it's an applied advanced version of some statistical processes. We also kind of dealt a little bit with machine learning stuff when we learned about data frames, because having data frames and matrices are, an important component of this stuff. So this chapter, guys, you're not going to be doing too much with code. There's no way we can get through everything we need to know about machine learning in, one chapter. However, I want to give you an introduction to this stuff. I want to give you some, good definitions, basic, understandable, practical lessons so that you can at least talk about this intelligently with other people and maybe find some more specific information later on when you are, focusing more on specific things, okay? So don't be too intimidated by this chapter. We will be going at it really light and kind of more just partaking knowledge than getting you to do too much intense things with machine learning. We will have one section where we do an example of random forests, but it's all very light. We're not going very extensive into it. It's more of a demonstration than anything. So in this class, guys, you're going to learn some high-level concepts about machine learning. I'm going to give you definitions like what is machine learning actually? What is this, like what are types of machine learning? What do we do with machine learning? How do we decide one machine learning model over another? I'm going to tell you about this concept of training and testing, which is how we build our machine learning models. It'll make sense once you understand the definition of a machine learning model. And then I'm going to give you some use cases, meaning I'm going to teach you about 2 or 3 different general types of machine learning models, but then go into why or when we use them and when it would be possibly useful for in a real world kind of setting. So there's going to be no coding section, but I'm going to be talking about the syntax of these things by using some interactives and some sketching, okay? So first off, what is machine learning? It's a kind of learning process. We call it learning, but it's like a statistical loop that takes some information and does some corrections over and over and over again. And we call that process learning because the way that things are updated and change within these models can be dynamic and make things not have like a static model. It can be changing depending on the kinds of information that are coming into it. So it appears to learn very stochastic, chaotic patterns that we wouldn't be able to just like apply a straight line to, okay? And it does this by giving it lots of examples to learn from, to, do its tuning and adjust and make tiny corrections over time. And so when we talk about training and testing, what we mean is we have a model, a framework for how we want to learn a piece of information or a chunk of information. And we want this model to try and find patterns within it. And how we do that is by giving it practice. It needs to have lots of different examples for it to learn from, because these machine learning models are actually kind of stupid compared to a human, where a human could take an example and like in 1 or 2 attempts be able to just figure out the pattern no problem. Machine learning models need thousands and thousands of different trials and tests in order to make work just right. So usually when we do machine learning, we need lots of data, which is the realm of data science when we have lots of information. So when we train our algorithms, basically all we're doing is teaching them or giving them information that we hope it's going to learn the patterns that we are looking for or interested in. When we talk about testing, usually what we're doing is we save a very small chunk of our data set so that when the algorithm is learned, we can use these values to see if it is accurate or learned what we wanted it to. So that's what these 2 terms, training and testing, are. They exist in basically all machine learning algorithms, where you feed in some data and you keep some aside. We usually call this process k-fold validation, meaning you have an entire data set and you get certain slices of it are used to test this information in an iterative way, okay? We can talk more about K-fold and maybe in our project, or look it up yourself. It's an entire process of like setting up a bunch of different training and test data sets that you then build and train your algorithm on successively and iteratively. Okay, guys, so the next thing I want to talk about are the 3 types of machine learning that exist at the moment. I kind of say 3 with a little sensitivity. That's why you see this question mark next to reinforcement learning, because there is still some debate over whether or not this is like an official quote-unquote type of machine learning. There's no point getting bogged down in the details of this, but it's kind of a new thing that's becoming more and more popular and like accepted more and more as maybe another way of doing things. But regardless of all that, guys, I'm going to be explaining to you 3 types of machine learning models. The first model I'm going to teach you is about supervised learning, and then unsupervised learning and reinforcement learning. And I'm going to spend, a good chunk of time talking about each of these successively, okay? So let's just do that without giving definitions for each of them and go through them one at a time. I'm also going to have a bit of a syntax thing as well. So supervised learning are used typically when you have a classification or a regression problem. What this means is you have a bunch of information that is like, let's take the example of a brain scan, and you have a bunch of a lot of brain scan information, and you asked your participant to raise their left hand or their right hand, and you recorded when they raised their left hand and when they raised their right hand in that data. Those labels are used to teach these machine learning algorithms the differences between those chaotic patterns. So if you had basically supervised learning means that it has all of this data, and you have labels that supervise, that tell the algorithm whether it got its classification later on right or wrong. And if it's right, it reinforces the patterns that it tried to execute in that iteration. And if it's wrong, it will inhibit that kind of pattern activation in later problems. So these support vector machines are really, really useful when you're trying to create classifications from complex data. Is this like political leaning, left or right, emotional information from text. Anything that you can have a label next to and a piece of data can be usually suitable for supervised learning. So let me give you an example of how supervised learning works. I'm going to talk about support vector machines in this, okay? And we're going to just draw this out a little bit so you understand what I'm talking about when we look at a support vector machine and how it works. Okay, guys, so in this example, I'm going to create just like some like kind of fictitious data, just like this, and we're going to have blue circles around here, and then I'm going to create a bunch of other information here, and we're going to draw this all out. So what that did not turn red. So what you're seeing here, guys, is a graph. I'm going to label these axes as well. But what we want to do is we want to create an equation that is able to create a boundary line between these red X's and these blue circles. I'm going to give these axes, it's just X and Y. It could be anything. We just know that these circles mean one group and that the X's mean another group, okay? We give them the labels 1 and 2, for instance. Now, it's really intuitive for us by eye to see how we create this boundary, right? This is a simple example. But if you were to think about a regression problem, like our linear regression stuff we learned, where we want to build a straight line through the middle of all this data to be able to determine the difference between things, it's not abundantly clear how you would do that with a linear model. Even other complicated polynomial models won't do this job very accurately. And if the complicated behavior is even more complex, so this is what the boundary would be obviously to us, a circle, but let's say, these graphs were distributed in a way that the boundary would be something like this. How would you possibly create a model for that easily? So what a support vector machine will do is it will take this information and it will apply something called a kernel. So it'll take all this information here and it'll run something called a kernel, which is essentially takes this information represented in two-dimensional space and increases the dimensionality. So it's represented in maybe three-dimensional space, and it's a lot easier for this line to be drawn. But that being said, guys, all of this information is used for training of a support vector machine, and you would need thousands and thousands of data points, and it would have to learn by, running different kinds of lines thousands and thousands of different times, okay? So basically what a support vector machine will do is in this case, might create a third dimension, which we would call Z. And then this data might be represented more as like a flat line. Let me show you this in like a slightly smaller graph here. There we go. And like that. Oh, here, there, and there. Maybe. There we go. Maybe now this information kind of looks like this, and it's kind of like a circle, almost like a cylinder around in three-dimensional space. Whereas these values are, lower. So you could create a straight line across this three-dimensional space that's a lot easier. And essentially what you can then do is convert this three-dimensional line back into a two-dimensional line that has these circular properties. And that's how a support vector machine will work. And that is a supervised model because we know that these are red X's, and then these are blue, that these are blue circles. They have labels associated with them, okay? Unsupervised models don't. So they just have, all they would have is just these, blue circles, and they'd have to try and figure out how much these things are related to each other. So let's go back to our slides here and talk about unsupervised learning a little bit. So unsupervised learning is good for what we call clustering and association problems. This type of data we don't have labels for one reason or another. Either A, they didn't collect them, or B, it's not abundantly clear how to create a label for this data set. And so what this kind of data does, or these kind of approaches do, is it tries to put patterns or pieces of data together, like pieces of training information. It tries to find the similarities between them and then cluster them together so that some are more related to others, and then also show how where the breaking point between different groups exist as well. So the common types of unsupervised learning that we know about or that we typically use in data science, I'm giving just a couple examples here, are k-means clustering and hidden Markov models. I'm going to show you really quickly what I mean by these like association and clustering kinds of things, all right? In this example here, what you see is this is actually a little bit interactive as well, is that we have all of these nodes, these dark circles, connected to each other. Blue ones tend to be more connected to each other than the other ones, but we do see some connectivity between these groups. So what this clustering and association algorithm is doing is it's saying that, these items in our data set are typically, behave similarly and act the same together, but a couple of these nodes have connections with others, and that they are kind of like a point of interface between other groups. You'll also notice here that blue is not connected to orange in any way, but orange is connected to two different groups, meaning it has more associations between them. So the way that these are colored and how all of these dots tend to are then organized together is how clustering and unsupervised learning work, okay? You use these algorithms that try and learn how related different groups are, even though it doesn't know what these groups actually are. It comes in without these things colored. It ends up coloring them for you. Okay, so that is an example of an unsupervised model. We're not going to learn how to build unsupervised models in this class, but it is a super important one, and it's kind of the alternative to supervised models, obviously. All right, everyone, so what did we learn today? We learned about the fundamentals of machine learning. We talked about the two basic types, and I hinted that there would be a third type, the reinforcement learning. We're going to squeeze that into a very quick lecture next. It's only about 6 or 7 minutes, guys. But we also talked about some foundational concepts of machine learning, like training and testing, when you use supervised learning and the kind of tasks it's really good for, when you use unsupervised learning and the tasks that it's really good for, and went through a couple of demos of that kind of stuff. Okay, guys? So in your next lectures, we're going to talk about, I mentioned reinforcement learning. We're actually going to do some machine learning. I'm going to teach you from the ground up the basics of a random forest model, and then we're going to talk briefly about deep learning. So thank you very much, guys, and catch you in the next sections.